complicated systems. So, in propulsion systems, reacting gas mixtures will generally refer to as combustion. And in general, and this is very important, it is hydrogen or hydrocarbons reacting with oxygen. Or air.
So simply, that's the key thing for propulsion. And if you look at all the way from car engines to rocket engines, it's the same exact principle, unless you're starting to do ionic-based propulsion, which we'll talk about at the end of the semester. But the general theme of propulsion, 95% of propulsion systems is combustion-based systems or reacting-based systems, and what you have to deal with is a hydrogen or a hydrocarbon of some sort reacting with air or oxygen. And therefore, so that's all I need to know as a propulsion engineer. I don't need to be extensively in-depth with the chemistry. All I need to know is I got a reactant mixture and I got a product. And the reactant mixture is composed of hydrogen, hydrocarbon with some air or oxygen. So I could say chemical reactions in general. So I have some coefficient multiplied by some composition of some sort, multiplied by a coefficient, multiplied by a composition of some sort, yada, yada, yada. And then I get some reactions, coefficient multiplied by a composition, and a coefficient multiplied by composition, and then it goes further. So what do I do here? Essentially, this is what we call reactants. This is what we call products. Most likely the reactants, as we just said, is going to compose of hydrogen, oxygen, hydrogen, air, hydrocarbon, oxygen, hydrocarbon, air. So I could say I have to deal with hydrocarbon fuels. So essentially this is the general form of chemical-based balanced reactions. We are going to pick what we're interested in a propulsion system. So hydrocarbon fuels. Now, hydrogen is not a hydrocarbon fuel, it's just hydrogen. But hydrocarbon fuels are primarily some carbon of some sort with some concentration level multiplied by hydrogen with some kind of concentration level. So, essentially, I'm after this for reaction. We're always burning hydrogen. And when you think of it as, well, what is the sun? The sun is actually extensive hydrogen reactions. So therefore, and it's interesting as you work in propulsion systems, you realize that and most actually energy-based systems, we're always after reacting to this. So it's very, very interesting that you're always after hydrogen. Carbon is just a byproduct for hydrocarbons. So what do I have as hydrocarbon examples? I have methane, CH4, methane, which is essentially your natural gas. If you have a natural gas-based heating system at home or so forth, that's a methane-based system. Well, we all barbecue, so we have propane most likely. So C3H8. And again, how many carbons do I have? Hydrogen, relative to hydrogen.
4.
These are carbon atoms versus the hydrogen atoms, so you have to leave it. Bless you. So let's take a look at what we put in our cars, which is C8H18 octane, which is, there's different blends. That's why you look at the concentration level. In reality, when you go and you have the 90-something versus 80-something at different gas stations, it's this plus how much additives we're adding to it, how much we're diluting it. Actually, it's a very good point. The refineries, so we talked about that hydrogen and CO2 mixture. That little stuff that gets mixed there, they say, well, that's how good of a separation that you're actually achieving by having that percentage. So when you're choosing and you want to understand why one grade is more expensive than the others, how you're separating. So like your colleague mentioned that question, how much entropy you had to, or work you had to do in terms of kilojoules to separate them, and that's why they actually cost more. So essentially this is blended for gasoline, blended with additives. Okay, and for us aero guys, jet fuels. Well, I have multiple jet fuels. Hopefully we do a lab tour in my lab